I think yesterday, today I'm gonna finish the microwave catalysis for ammonia synthesis, and then there will be the case study, and then today there will be 3 sessions, so it's gonna be a long day. I know you have the session before already, so there will then followed by the case study. Case study means we need to calculate with a 100 megawatt solar or wind farm, how much ammonia we can make. And then also I'm also going to show you how you calculate the ammonia conversion and how do you analyze the ammonia. So when I said, if you have a microwave reactor or any reactor, how conventionally in a laboratory you measure ammonia by gas chromatograph, FTIR, or any method. Okay, so that's what we need to talk today. And also, if I have time, I'm going to talk a little bit about the cold plasma. What is the cold plasma? So I think yesterday when let me share the screen. Can you see my screen?
Yes, sir. It's visible.
Okay. So yesterday when we talk about microwave catalysis, I think one of the audience is saying, yeah, microwave can generate plasma. Yes, microwave generate plasma is different from cold plasma. It's a hot plasma. Okay, so I'm gonna leave it for the next session. We can talk about the cold plasma. Okay, let's finish the microwave. So yesterday we talked about this curve, so-called why on the microwave when you use the catalyst, the different curves. So on the right hand side, if you can see it, my question is, can catalyst change the thermodynamics, equilibrium position? The answer is no. But why we have 3 curves? So basically, this tells you when microwave interact with the surface. Let me go back. So if you look at the microwave interacting with the surface, this is basic catalyst surface, okay? Under micron scale or even nanometer scale, there are so many localized, like this, localized the hotspot or center. So the basic temperature on the surface is not uniform. It's selective heating. So what does it mean? That means if you look at the reactor as a body by itself, it looks like it's one temperature. However, on the catalyst, it's just different temperatures. It's all over the place. There are millions of the places. The temperature are different. So that's why it's a non-equilibrium. So on the catalyst surface, if you look at it on the micro scale, it's non-equilibrium. So that's why when you measure the equilibrium, you see the different curve. So yes, that's how the microwave works. So this is very complicated theory behind, and then we publish the paper. So we are still trying to understand what happened on the surface. So you basically need in situ tool. In situ means you need some kind of measurement, measure the real time, what's happening on the surface. That tool is available. Is in situ Raman or in situ SPS, so you can see the surface. So anyway, so I'm trying to tell you this observation experimentally, but to interpret the phenomena, you need a lot of the evidence. Okay, so all right. Again, as I mentioned, if you have any question, please interrupt me and then ask me the question. Okay, I may stop from time to time and then ask you questions, but feel free to interrupt me. Talking about economics, so if you let me put it this way. Traditional Haber-Bosch process is high pressure, high temperature. So if you remember the flow diagram I show you, in the back end, there's a high pressure cryogenic condenser. So that's the commercial, the standard operation. Since we use the microwave, we lower the pressure. The pressure is not going to be 250 bar. and it's only like the 10 bar. So below the pressure, we should not use those high pressure separation. All right. So you may be wondering what we use in there. Well, there are many technologies you can harvest ammonia. So let me have a blank sheet I can interpret you. Hold on. I'm gonna have a new slide. Okay. So this is your reactor, and then this is I would say let me see let's say this is the ammonia reactor. Okay. So basically you have the nitrogen coming in. Your hydrogen nitrogen coming in, and then you have let's say the ammonia coming out. Okay. So keep in mind when ammonia coming out, there are the unconverted hydrogen and nitrogen. All right. So because it's in equilibrium control, that means hydrogen nitrogen come in, they never get 100% conversion. So you always have a mixture of ammonia, hydrogen, and nitrogen altogether. So that's why you need to go through the separation. All right. So when you go to the separation, so traditionally you go to the cryogenic separation. All right. So now with this high pressure, so this is the basis of a Haber-Bosch process. So since we lower the pressure, you don't have to go to the Haber-Bosch separation. So we basically eliminate. We basically use I would say solid solvent. So the whole idea is you want ammonia stay here, and then and hydrogen nitrogen recycled, all right, and to recycle. So there's some kind of the solvent or the what we say liquid what do you call that, liquid liquid acid, and there are different ways you can do this. So the reason I'm showing this is there are different ways. It's called I would say the low pressure separation. Okay, technology here. So you can list the number of them separation. So this is what we do. And if you go by here, so we have 7 cases. Case 1, case 2, case 3. So in these 7 cases, the what do you call that? The separation are different technology. If you look at the pressure, the separation is from 80 psi to 500 psi. It's a low pressure separation. So we compare with the base case. Base case is Haber-Bosch cases. Base case is high pressure. It's basically the PSIG is in US we use PSIG. So one bar equals to like roughly 15 psi. Okay. So but regardless, this is really the if you look at my cursor, this pressure is Haber-Bosch pressure, and then we have 7 cases using different separation technology, and then but there are low pressure separation. Low pressure separation, obviously, you save a lot of the capital, all right? So then we run the a simulation, Aspen simulation. If you work in the world of chemical engineering, there's the software called Aspen simulation, and then you can simulate the process to see how much the capital, how much the I would say the operating cost. So that's we have 7 cases. I don't want to go through the one by one. It's the bottom line. All this case 1 through case 7. Only difference is they are the back-end separation. Sometimes they use the so-called solid solvent. Sometimes they use the molecular sieve, pressure swing. It's all different technology. We separate ammonia. And then we compare with the base case, which is the high pressure separation. It's Haber-Bosch cases. Okay, make sense? I want to interpret it. I'm going to ask the question. I just want to hear yes or no. Has the audience, can any of the audience tell me if you ever heard of Aspen simulation software? Let me put this. Yeah, can you give the microphone to anyone? I want to know. Anybody just say yes or no. That's why I want to know. Have you ever heard of Aspen simulation?
Aspen simulation. Aspen simulation. Sir, we are working on that RSM and ANN.
So see my typing here. Has anybody heard about the I'm pretty sure in your university some the department like they use the Aspen simulation software. Have you used the Aspen simulation software?
We are working on the COMSOL software, sir.
Okay, thank you. So you do their student know you do know Aspen simulation. That's good. Okay, so basically we use the Aspen simulation software and then putting the process together to simulate. So okay, go ahead.
Sir, actually, we are using Aspen Plus software, sir, for simulating the plasma gasification process.
Which software can you repeat? What's the name of a software?
The Aspen Plus only. We are using Aspen Plus software for simulating the thermochemical conversion process.
Okay, so you use the Aspen Plus. Okay.
Yeah.
Yep. Yes, that's what we use. That's what I mean. Okay, good. So that I'm so glad you understand the Aspen. So we basically have 7 cases we using the Aspen simulation software. So the result, I'm going to show you the result. Okay. So I don't want to go through how you set up the Aspen simulation unit operation, but this is the result. And then so basically, in order to compare this is 7 cases, which is the microwave ammonia synthesis compared to the base case, Haber-Bosch cases high pressure. And then we have to use the same standard terminology. It's called the minimum selling price. So typically in economic analysis, you use the minimum selling price. What's minimum selling price? That means from any of the process, you come up with a unit cost of ammonia, which means in order to produce 1 unit ammonia, how much the price you can sell. So which means in order to make profit or in order not to lose money, you have to sell at this price. That's called the minimum selling price. You follow me? For example, even for base case Haber-Bosch case, basically the base case for Haber-Bosch case, and then you have to sell the ammonia at 11 cents to 13 cents per unit of ammonia. This unit of ammonia is not by weight, it's by the energy. So the per unit ammonia means 1 unit of ammonia carry the energy of for the 1 kilowatt hour. So which means if you take ammonia, measure the energy content is equivalent to 1 kilowatt hour, that's 1 unit. So it's a very complicated concept, but that's how the department, because this project come from the Department of Energy, that's what they want to use. They want everybody to calculate 1 unit of ammonia, which is 1 kilowatt hour of unit, how much the minimum selling price. Okay, so we do this Aspen simulation. In Aspen simulation, you have to have the so-called plant capacity and raw material cost, utility. Utility means you have to, in order to run the ammonia plant, you have to have a recycle and the compression and also the electricity cost. Is that right? So those are utility costs. And also you have to depreciate. Depreciate means you put a capital on it. Every year you have to depreciate. So all the capital and depreciation costs, utility, roll them together. You come up, aspect simulation will tell you what's the minimum selling price. Okay, so that's why I did a quick survey. I want to make sure there are some students understand the aspect simulation. It's a very powerful simulation tool. And the industry, when I work for industry, we use that software because that software gives you a lot of the cost module, which means how much it cost for the pipe and for the distillation column, and then there are a lot of the I would say the cost model called Icarus in there. Anyway, so typically the base case in the Haber-Bosch case to produce 1 unit ammonia is cost somewhere around 11 to 13 cents. But if you look at the microwave, the catalysis, and then there are some cases you can the minimum selling price is lower. The lower of a minimum selling price, the better. You follow me? So that means you can make a profit if you can sell above that price. To say different way, if my minimum price selling price is 10 cents per unit, if a market want to buy my ammonia at 20 cents, oh yeah, I love to sell. That right? So that's how you gauge the minimum selling price. You basically set your bottom. I'm not going to sell this below this price, but anybody offer me a high price, I'm going to sell. You follow me? So that's called the minimum selling price. So if you look at all 7 cases, some cases are similar to Haber-Bosch, but some are higher. Like case 1 is 12 cents, but still within range. So all of the 7 cases, if you look at it, they are within the range of the Haber-Bosch. Keep in mind, Haber-Bosch has been there for 111 years. They built very large. If you have the microwave unit, at a modular scale, which can beat Haber-Bosch price, that's you win the game. You follow me? So a lot of people say, oh, Haber-Bosch is 11 to 13 cents. What if you sell 5 cents? That's not going to work because there are a lot of what you call that the improvement that Haber-Bosch has done already for over 100 years. So it's pretty hard for the new technology to outperform too much. As long as we are lower and or similar to Haber-Bosch, that's what you want because this new technology Haber-Bosch cannot scale down. So that's why in about a few minutes we'll go into the case study. The case study will tell you, with renewable power you can do very small scale, whereas if you scale down Haber-Bosch, it's going to be more expensive. Okay, so to say a different way, if you have Haber-Bosch technology, let's say now we have 7 cases. If you will put in like a case number 8, Haber-Bosch, it's going to be higher because it's not matched with a low pressure separation. Okay, so I'm going to shift the gear. This is basically Haber-Bosch technical economics. We published a paper already. If you are interested, I can show you where we published the paper. It's a lot of work by the professor, the collaborator at the WVU. His name Dr. Dibangsu Bhattacharya. So you can hear the name, the Dr. Bhattacharya, and also originally came from India. So he and I work on technical experimental side. He work on simulation side. So I'm going to switch the gear to the using the methane plus nitrogen. I think one of students mentioned about, hey, some company in India using the ammonia, natural gas instead of hydrogen. So that's what I'm going to talk about. Before I shift the gear, anybody has any questions so far on the microwave? How we use a microwave to improve the Haber-Bosch process. We lower the pressure, we lower the temperature, and then we are down tactile economic analysis based on the process simulation. And the data are coming from our laboratory. Anyone have any questions before I move to the next? Okay, let's move on to the next. So if you remember, most of the Haber-Bosch plant in the United States, the hydrogen coming from steam reforming of methane. And then true, in some other part of the world, and then the hydrogen coming from the co-gasification is even more expensive. So give or take, if you hydrogen and coming from the steam reforming, so the capital cost is probably 50%. 50% ammonia side, 50% hydrogen side. But if you hydrogen coming from co-gasification, so in terms of the percentage of cost, by the total cost will be high, but your co-gasification and hydrogen cleanup will cost you probably 70%, 70, and 30% of ammonia. So it's a lot of the cost on hydrogen production. So if you use the electrolysis, the cost even more because of you have to scale up electrolysis and also the cost of the what you call that the whole system. So that's why the electrolysis has not been utilized for ammonia synthesis because electrolysis hydrogen cost, the capital cost is so high. So now the innovation will be, okay, what if I don't use hydrogen, I use ammonia? Then you have to know nitrogen will not react with methane directly, even if I write the equation like this. But essentially, the reaction doesn't go this way. So you have to produce hydrogen. So this is called the overall reaction. I'm going to show you experimental data, okay? Like this. So but essentially, you have to have methane. So this reaction called the methane coupling. Methane coupling means you have two methane, you make ethylene, and plus two hydrogen. So this is hydrogen you are using. I don't balance in the interest of time. I don't balance the equation. I just want to show you what's happening. So, okay, so these two reactions adding together, you become the ammonia synthesis. So this ammonia synthesis produces the what is called ethylene, ammonia. It looks pretty good, but it's challenging. I'm going to talk about pros and cons. Why Haber-Bosch process going this way, and then what's the benefit? We are going to get this. What's the challenge? Okay, you will see the challenge. Activating the methane and the nitrogen together is a challenge. Okay, so this is what we need to talk about. Okay. And also it's done by one of my students. Actually, two of my students. One is they both came from India. I think one is my postdoc from IIT, Tuhin Khan. I think they both went back to India. Tuhin now is working for one of a national lab in northern part of India. So he did all this simulation. This is basically in order to have this reaction, we want to see if theoretically it's going to work, which means in theory we put the methane and the nitrogen together, and then based on the DFT, the simulation is going to work. I'm not going to do the survey. I will tell you what the simulation we do in here. I'm pretty sure some folks it's called the DFT calculation. So it's a dense function theory. So DFT stands for the dense function theory. It's from the physics, but we use it for the chemistry. So it's very popular now if you're familiar with DFT calculation. By doing DFT calculation, we want to know, hey, what catalyst we need in order to activate the methane and the nitrogen together to produce ammonia and ethylene. Okay, so the DFT calculation tell us it's feasible, and then and basically the some certain catalysts under the so-called active phase, they can produce ethylene, ammonia, and hydrogen together at 487 degrees C and ambient pressure. So this is really encouraging. And then we basically start making this catalyst. Catalyst is a potassium ruthenium catalyst, and then we make a catalyst, we start running the reaction. So this is basically the experimental data under microwave, and then you can see the methane conversion, and then the begin very high and then drop. So the high methane conversion means if you have methane conversion, it turns into the hydrogen and the ethylene. You can see the on this reaction, we run at a different temperature, 500 degrees C, 550, 600 degrees C. The three temperature on the methane conversion, then we monitor the hydrogen concentration. That's what we want. The reason being that you need to have a hydrogen in order to react with nitrogen to run the to make the ammonia. All right, it's not just like a methane molecule collide with the nitrogen reaction. Is you had to go through hydrogen and the hydrogen react with nitrogen. So this is a good sign. Based on our simulation, based on our experiment data, we know, okay, we do generate hydrogen, and that hydrogen should react with the ammonia. So this is what we do. Then the next experiment, we found out we have on the right-hand side, we saw acetylene, ethane, and ethylene. So this so-called methane coupling. It starts from methane. So when methane couple together, they release hydrogen. When they couple together to form ethylene, there are two hydrogen released. If they form acetylene, there'll be 4 hydrogen released, and with ethane, that's 1 hydrogen. So basically regardless, when methane couple together, either form ethane, acetylene, ethylene, they release hydrogen on left-hand side, and we are very happy, we found ammonia formation. You can see based on the different temperature, we observe ammonia produced. Okay, so this is a very encouraging result. I think we published this paper already. So then we did microwave with a plasma reaction. So if you recall, let me go back. If you recall what we talked about yesterday, so microwave, we can run 2 scenarios. One scenario is microwave catalysis only. So that means the methane and the nitrogen coming in, they interact with the catalyst, and then there's no the plasma. So that's what you saw. We produce the ethylene and we produce ammonia all together. We also run another scenario, which means still under microwave, but we generate plasma first. That means the nitrogen and the methane form the plasma. Then plasma flow onto the catalyst, and then start reacting. Okay, so I'm talking about this scenario already. I'm going to talk about this scenario. Let's say this is called a microwave only. This is called a microwave plasma. Okay, so let's go back. So this is all the DFT simulation. We run first microwave only. We saw methane conversion, we saw hydrogen, and this microwave only. And then under microwave only, we saw the ammonia. So we achieve our goal. Now I'm running the microwave plasma, okay, to see what's happening. So this is the data really show the microwave plasma. So if you look at the microwave plasma without catalyst, we produce a lot of acetylene. Keep in mind, what we want is ethylene, all right? So we produce a lot of the acetylene, but we produce the HCN and also the blue the ethylene. But you don't see the ammonia. So when we run the catalyst only thermal, not microwave, and then we do not see the hydrogen. This are in the middle, the catalyst only. Without, it's all the baseline, which means we run conventional, and then see what's happening. So finally, we run microwave plasma with the catalyst, which is the scenario I show you on the right-hand side. And then the good news is we saw a green bar, which is ethylene, and then of course acetylene, and also ammonia. So this is really encouraging that under two scenarios, in both scenarios, microwave only, we saw ammonia, acetylene, and then when we run the a plasma, we saw the same thing. Okay, so this is very encouraging. So we can talk about the energy consumption on the microwave and plasma. So microwave only is more efficient because we do not need to ionize the molecule. We just activate the catalyst. So that in the gas phase, there's no plasma. Now, when we increase the power, and then we basically turn the methane and nitrogen into plasma to begin with. Remember, we elevated the beginning the energy, so it's easy for them to cross the I would say the energy hurdle. All right, so that's a different approach. And then we also produce ammonia. But true, in both the scenario, the energy consumption or the power consumption they are different. It just depends on your objective. Okay, so before I'm shifting the gear, I know today I'm moving fast because we are behind my planned schedule. So I want to finish microwave. So I'm going to move to the case study and also the some other topic related to the green ammonia. Okay, so I'm going to stop here. Let's spend a couple of minutes to summarize the microwave catalysis, microwave plasma catalysis. Anybody have any questions before we move on? So I'm going to go back to the curve. So basically, the microwave, you can run two scenarios. Based on this, any student have any questions at this moment?
Sir, and that bar chart you shown last.
Okay, I'm going to show. Okay, go ahead.
In which we are directly synthesizing ammonia from ethane and from ethane. Hello.
Say it again. Yeah. This is direct. Yes, this is direct synthesis from methane. Yes, the feedstock here is methane plus nitrogen. Yes, it's direct synthesis. Yeah.
Yeah. Yes, sir. Here you mentioned the plasma plus catalyst. Is this plasma catalysis or post plasma catalysis?
Yes, it is. So on the right hand, that's why I keep on going back and forth. So on the right hand side, this bar is the scenario here. It's a post plasma. Good question. Yep. So that bar is this scenario.
Yeah, sir. The post plasma. Yeah, okay.
Yeah, the post plasma. Yep. It's generated by microwave. This is not cold plasma. It's not DVD. Cold plasma doesn't work this way. Cold plasma, this catalyst is in the center within the plasma, in the plasma range. But this post plasma, that means you generate plasma, light plasma going onto the catalyst. The catalyst is outside the plasma zone. So this is different from cold plasma. Yeah, you follow me? Yeah. It's microwave plasma. Any other questions? Very good question. So I'm glad that you understand the post plasma. Yep. Okay. So if you don't have any questions, so we end the microwave catalysis. So I'm going to stop sharing. Let's go to the case study. I sent one slide to the Dr. Anand. I think he distributed to you, but I can show you. The what's it called? The slides. Okay. I'm going to find my slide. So that give you a condition. If you haven't read that slide, I will give you probably a couple minutes to read. But first, let me find the slides. Okay. Okay. I'm going to share this with you. I'm going to put on the screen, and then if If you have seen this slide, you have done enough homework. I want somebody to tell me how you did the calculation, and then show the whole class how you analyze it. Okay. So this, can you see this slide?
Yes, sir.
Yes, sir.
Okay. So there's a problem. So basically, in US we call this the. I think you call the case study. We say the problem case problem-based learning activity. Okay, so it's basically I give you a problem. I hope you learn something. So that's called the problem-based learning activity. So it's called a PBL. Okay, so conditions. If you have a 100 megawatt, it's called a nameplate. Remember I talk about anytime you talk about solar and the wind, you basically you talk about nameplate. You got to be careful. And then the 100 megawatt. That doesn't mean that they can really generate the 100 megawatt the power at in the average. So you have to look for the capacity factor. I give you capacity factor 30%. That means if you this the solar and wind farm operate, let's say for a year, so it's gonna be 100 megawatt times 30%. That's all you get, because the solar will never run 24 hours and 7 days, and then the windmill will not spin all the time. So there's a capacity factor. It depends on how good the sunshine, the location, and how good the location of the wind. So, but I give condition 30%. Yeah, so that's use the number one. Number two, the bullet point, we plan to use the electrolysis to produce hydrogen. So with this the energy, so you basically have an electrolyzer, and then you put the microwave in there, you generate hydrogen. I also give a condition. So to produce 1 kilogram of hydrogen, you need about 55 kilowatt hour. Okay, kilowatt hour is energy. Okay, it's energy unit. Megawatt is a power unit. So you have to turn megawatt into the megawatt hour or kilowatt hour in order to calculate hydrogen. I'm sure you understand. Okay, so basically you need this much of energy, 55 kilowatt hour, to produce 1 kg hydrogen. The third bullet is the hydrogen. So once you have hydrogen, you want to make ammonia, right? So you have to use this the equation called stoichiometric equation and to make ammonia. I'm pretty sure you do not need college knowledge. You simply do energy balance and then the mass balance, you will come up with the answer. So assume there's no utility consumption. So just assume your hydrogen will go to the ammonia, but actually a lot of this megawatt will not go to hydrogen. You have to have the power set on the side to run your condenser, to run your pump. But let's eliminate that. Let's say, okay, I don't need those. I just want all this power, capacity factor, to make ammonia. So, okay, question number one. I want everybody to do the quicker calculation. Calculate how many kg ammonia this 100 megawatt solar farm can produce in 1 day. The time is 1 day, 24 hours. Okay. So then question two, Haber-Bosch plant was built at a very large scale. The capacity is over 1,000 tons per day. So based on your calculation, and then how do you compare your calculation capacity with the Haber-Bosch capacity, and what's your thought behind? I think that in the last of 3 or 4 days, I would kind of, teach you or give a lecture. Haber-Bosch and renewable power, they're a mismatch. But I want you to use the data to show where is the mismatch. Okay, I'm going to give you 5 minutes, and then whoever ready, please give him the microphone. Tell me the answer. Tell me how you calculate. Great, go ahead. 5 minutes, okay? I'm going to stay here. If you calculate already by home, just tell me the answer.
Sir, I have one answer, sir. I worked at home. I got 74.089 tons ammonia.
Thank you.
Number one.
Wow. So you got 70 tons per day.
74.08.
Thank you. Wow, perfect. You should get A+. Let me see my calculation. Wow. I'm glad I sent you. I'm glad I sent Dr. Anand, so we save time. We don't want to waste the 5 minutes here. I'm going to see my calculation. I did have Excel spreadsheet. Hold on. It is. I think it is seven. It is about 70. So let me see the case study. It's in one of my. I have Excel spreadsheet somewhere. Yeah. So anyway, I think my Excel sheet buried somewhere. So can you just tell you how you come up with it? It should be very simple. Just tell me how much tell me the breakdown, how you did the calculation. Okay, go ahead.
Yeah, I can tell that. Initially, I started from nameplate solar farm. So nameplate to I applied capacity factor. So capacity factor in the sense nameplate power.
Yeah.
Actual generation by nameplate power. So it will give capacity factor. So actual power output is calculated from
Yeah.
nameplate multiplied nameplate power with capacity factor. So I obtained 720 megawatt hour.
Yep.
It is
Keep on going.
calculated for 24 hours. So I taken 24 hours out of that I got 720 megawatt hour. 720 megawatt hour we can generate per day from that plant, from that solar plant. So afterwards that 720 megawatt hour electricity is used to produce hydrogen.
Yep.
Because we are not considering any other power which was used to generate ammonia. In that condition, you are not mentioned any power requirement for producing ammonia from nitrogen and hydrogen. Only mentioned only hydrogen generation alone needs power. Like that, it mentioned in condition. So all the power utilization is for producing hydrogen. Once hydrogen is produced, then directly we can take that hydrogen for ammonia synthesis. So we are not using any resilience power.
Good. Very good. Okay. So basically, the answer is about 70 ton per day. All right.
That's, 74. I got
okay. So all right, I need to go back. Thank you very much. So I need to go back to my slides because actually I'm going to. Okay, so I'm going to somehow my screen freeze. Okay, so I need to find my slide. Okay, here we go. Okay, so now I'm come back to this slide. Very good. Thank you for. All right. So you can see this is the slide. All right. So it's very good. So now you can see the 100 megawatt the solar farm or wind farm actually is quite big. Remember, I think the largest one I saw in the United States is about I think somewhere close to 200 megawatt. So in Australia, somewhere you can see probably 1 gigawatt. So that's huge because they put up so many. So now you can see how the challenge of the renewable power. All right. So basically, you only barely produce the 70 ton per day ammonia, whereas the Haber-Bosch plant, the smaller the Haber-Bosch plant is 1,000 tons. So if you borrow the technology, 100 years old technology, try to scale down, it costs you more money. All right. Now, by the way, I think that this student mentioned that the 70 ton we are not assume the utility, the consumption. If you factor in utility consumption, that means you do not have the 100 megawatt to begin with, because I would say a fraction of this the 100 megawatt you have to keep on the side to run your pump, to run your recycle, to run your all the utility. Probably you barely end up with 50 megawatt in there. So, what does it mean? That means you probably will not produce the 70 ton per day. You probably produce 40 ton per day. So it's very small. Okay. So this basically force you have to think about out of envelope the technology. What's out of envelope technology? That's what we are talking about in the courses. Microwave, electrochemical, which you can basically the miniature and then the so-called modular instead of building bigger. And then all this technology, actually, they have, if you make a microwave or electrochemical larger compared to the Haber-Bosch, it's challenging because you have to scale up the microwave equipment, you have to scale up electrolyzer, you have to scale up the plasma, the reactor. But to think of differently, all this new technology, they are more suitable for smaller scale. That's called a modular scale. The key is you have to have some kind of innovation or the change. What's the innovation? Low temperature, low pressure, so you can become more efficient. We talk about so much of green ammonia, but for the manufacturer or end user to adopt it, it's still economic, all right? If you say so many things good, oh, this is green ammonia, but if your ammonia is from microwave or electrolysis and costs more than the Haber-Bosch, they are not going to buy, all right? Remember the table I show you. So Haber-Bosch is from 11 to 13 cents per unit for the ammonia produced. But for the microwave, we are probably in a similar range or lower. That's what you're looking for. Okay, so true. If you try to educate the public about green, oh, I'm doing the green, but by the way, I'm selling higher price than the Haber-Bosch, nobody buy because ammonia produced from Haber-Bosch and the ammonia you produce from the renewable power, they're the same in chemistry, all right? This is different from the bio. The bio is different. So I'm talking about biodiesel or the biofuel. They are different in terms of the chemistry or chemical formulation. But for ammonia, it's the same thing. Okay, so you have to watch the economic. So I'm glad you have done the homework calculation, but keep in mind this is really rough calculation. But in reality, when you run the aspect simulation, remember economic, you have to pay the utility. They basically, when you set up the process simulation, every unit you have to put in the utility. So this 100 megawatts probably will not last long. You barely have a little bit to run the electrolyzer to make a hydrogen. Majority of this probably will go to the utility, recycle, and then condenser. Okay. Anybody has any more questions? I know we have a couple minutes to end this session. So before we end, I want to basically ask you a question. Let's talk about where's my, I lost that flow diagram. Anybody has any question here? I think it's clear, all right? This is a very simple exercise, makes sense, all right? So basically from different angle or semi-quantitatively, you don't want to scale down Haber-Bosch the technology to fit into the microwave, to fit into the electrolysis in order to utilize the renewable power. So you have to have some innovations. Okay, so I'm stop sharing here. I want to go back to my original diagram, so that will save me time.
Sir,
go ahead. Question. Go.
Yeah. So in that question you mentioned about scale down. Previously we have discussed about scale up rule. 0.6 rule we discussed.
Yeah.
Similarly, scale down, how we can do this? We don't have knowledge about that because we usually do in our lab scale up only. Scale down approach, how we can do that, sir? We want to learn something.
Yeah, I think the 0.6 rule is really very rough engineering in the engineering world. So remember I showed you the calculation, all right? So basically you have a capacity and then you divide, if you scale up, if you double the capacity, doesn't cost you double what you call that, the capital. If you scale down, by 50 times, it doesn't, you do not save capital 50. So those 0.6 power rule is a very rough engineer calculation. We call that the rule of thumb. But if you really do real world engineering, so I used to work in it's a company called Black & Veatch, and actually Black & Veatch has a branch in India. So I used to deal with a lot of the colleagues in India. I think the city is called Pune, Pune. Is that the city in India? So Black & Veatch has an engineering firm in there. So we used to do engineering, but the real world engineering, you should do this. You run the process simulation, and you set up the process, run process simulation, then you size each unit. Each unit means how big of your condenser, how big your Haber-Bosch reactor, how big your pump. So that simulation will tell you how much you need. Once you size those, they will tell you how much utility costs. So once everything done, there will be there's a software package in Aspen. I think it's called Accurus. Accurus means they basically apply the price. So you have to be careful because after the pandemic, the price has gone up. Whatever the Aspen, the price telling you, if you go to market to buy, it's going to cost more than that. So in the real world engineering, instead of using the cost model from the Aspen, we have to get a vendor quotation. Vendor quotation means you have to call every manufacturer saying, oh, tell me how much this compressor costs, how much this circulation pump costs. You have to call. Otherwise, the Accurus, the software will not give you a good answer. They do update from time to time, but that's not real. But even today, if you look at my house, the water pump, for the swimming pool doesn't work, and then I have to go to buy it. Well, that cost a couple of years ago, you are talking about probably a couple $100. Now it's over $1,000. So that's the key. Anyway, so basically you run simulation. The key is you have to size each unit, and then once you size unit, that's called the easiest. The unit to size is a distillation column. Distillation column very simple. You basically pay the metals and pay the vibration cost, installation cost, and then once you put together, you have total capital cost. Okay, operating cost is basically the rule of thumb. You have to have Excel sheet, how many workers you need, what's the labor cost, right? In India, let's say if one worker costs you, $30 per hour, you factor it. So there's a lot of calculation. The table I show you, economic, it's a lot of work. When we summarize that table, you are talking about it's probably a year, 2 years work. We do the simulation. That's why I mentioned the gentleman, my colleague, Dr. Dibangsu Bhattacharya. He did a fantastic job to do all of this. So anyway, when I say the 0.6 rule, that's a very simple rough. But in the real world engineering, you have to run all the simulation, all the cost estimate. So that's the basis called engineering design. Yeah, and in the world, there's so many the so-called EPC firm. EPC means engineering, procurement, and construction. They do this for living. The company I mentioned called Black & Veatch, they have a branch in Pune, I think, in India. And then they do. I used to work for a company. I work in the headquarters. So they are EPC firm do all this. It's very complicated. That's why I think in the day one I asked you to estimate 1,000 ton per day ammonia plant. If you build in US, how much it's going to cost? It's $1 billion. But I can tell you how much it's going to cost to build in India. It's going to cost you $0.8 billion. The reason being that only thing you save is the manufacturer installation cost, because in US installation cost is expensive, but in India it's a little cheaper. But still, $1 billion here is $0.8 billion in India. I can tell you for sure because I used to do the work with teaming with Alliance in India, so I know how much the labor costs. So anyway. So I hope I answer your question. It's not simple. It's not just simply 0.6 rule. It's a lot of the calculation and the simulation behind.
Yeah.
Okay.
Yes, sir.
Make sense?
Yes.
So I think when we I tried. Very good question. I tried to find but I think when we come back to the next session, we will go through I want to show you, if you have ammonia, how you do the measurement. In the ammonia plant, you take a sample, you go to the central laboratory, but in the laboratory, constantly you have to take the data because we are doing research, all right? In the manufacturer, you probably take maybe 2 samples per day because that's a standard operation, Haber-Bosch. But in laboratory, we do research. You have to take the data maybe every second, every 2 seconds. I want to show you available tools. Okay, so I don't think the audience has experience on using all kind of the analytical technique to measure ammonia. Then we will do another exercise on how you measure the ammonia concentration and back calculate the so-called ammonia conversion. All right, so I think that we will have 1 hour break. All right, you guys will go to lunch, and then let me see the schedule. So it's I think we have do we have a 1 hour break? Is that right? Correct?
Yes, sir.
Yes.
Okay, so I will see you after 1 hour. Okay, thank you, everyone. Yeah.
Thank you, sir.
Thank you.
Thank you.